capable of producing this type of forecast right now. We almost did not fly it, actually. We had a daily teleconference to make a decision about aircraft operations. We'd already flown Erica, Marty, and Joaquin, and I'll talk about Marty a little later on, but it was a weak hurricane that formed in this approximately the same area and then went into the coast. We thought this same thing might happen with Patricia. Some of the models had it spinning up very quickly and then just running into Mexico and nothing happening. When we finally did make the decision, actually, fortunately for us, we had another group that wanted to do some stratospheric chemistry experiments or some other experiments. So they had also payload on the aircraft. So they wanted to fly the storm before it, or while it was a depression or early. So they contributed flight hours. I think if they had not said that they would contribute the flight hours, we might have waited. But instead, we decided to go, we got lucky. Also, NOAA P3 decided to deploy, and so once we had another aircraft, and that made it also very attractive to go and fly. But as I said, on the 18th, when we were trying to look at this, we really had no idea that this would happen. And then even on, so this is the forecast from 6C, 21st October. So that's right here. So we had about a 35 knot, about 35, 40 knot storm. This is all the intensity guidance. So several of the intensity was suggesting a reasonably strong storm, but nothing anywhere close to that. I mean, it's just a spectacular deficiency in the models to predict this type of intensification rate. So it ended up not only setting a record for the fastest intensification rate, the 185 knots is the strongest in the Western Hemisphere, so strongest in the East Pacific or Atlantic on record. It may be one of the strongest in the world, but we don't have aircraft reconnaissance in the Western Pacific, so there. I think Typhoon Tip still holds the record for strongest storm, but it was also much, much bigger. This was a very tiny storm. So if you look at the forecast errors for this storm, this is 12, 24, 36, and 48 hours. So I mean, the 12-hour forecast, you would think that that might be pretty good, but in fact, the 12-hour forecast error was 65 knots, 75 knots, 95 knots, and 105 knots for 48 hours. So these, even with the 12-hour forecast, we still have many challenges. Now, fortunately, all storms aren't like this, right? This sets, as I say, it sets a new bar. It tells us what the upper, and hopefully the upper limit of the intensity problem is. And obviously, statistically, we can do much better than this on most storms. But it does, I think, highlight the challenges. So I just wanted to use that as a bit of a motivation for today's talk. Okay, so let's talk a little bit of theory, and then we'll get into some observations. I showed this the other day, but we've kind of thought about the hurricane intensification problem as a Carnot cycle for many years. So this is from Emmanuel's classic 1997 paper, where he makes the assumption that the hurricane is largely axisymmetric, so no variations in azimuth, largely in gradient wind balance, so pressure gradient force balanced by Coriolis and centrifugal force, okay? And then hydrostatic balance, vertical pressure gradient balanced by gravity, right? And it turns out these are actually quite good approximations on average for this tropical cyclone above the boundary layer. And if you make that assumption, then you can do some wonderful mathematics that he did to simplify the problem and to show that essentially, as you take air inward here, if you think about this as the first leg of a Carnot cycle, isothermal expansion, as you pick up heat, you gain heat from the ocean surface, and then adiabatic expansion in the eye wall here, and then this leg is a little bit tricky in the real atmosphere of isothermal compression, or basically something like radiative cooling, and then a adiabatic compression, and then the cycle starts all over again. But during this, work is produced, and we generate kinetic energy of the swirling flow, right? Now this is a bit of a thermodynamic picture of how that might happen, right? And we know that that's the case. We know that we need warm energy from the ocean surface in order for the storm to form. Without that, it's difficult. But I think...
excuse me.
Yes, go ahead.
This assumption is Carnot cycle, but recently, for example, Hacking 2011, he reported that the Carnot cycle is incorrect for the tropical cyclone intensity. So, what do you think?
That's a good question. Actually, we've been looking at this as well. Some of Hakum's work where he's looking at the really long integrations of the axisymmetric model. Yeah, I agree that the Carnot cycle is an incomplete model of the tropical cyclone. I think it's a good sort of zero order or crude approximation. But as I already sort of mentioned, this leg doesn't really happen in the atmosphere. And in fact, it's unlikely that this same air parcel is recirculated, right? It happened in Greg's paper, Hakum's paper. He does show, if you trace it out over many, many days, you can get something that looks sort of like this, right? It's not a true square in the Carnot box, but you get something that's like a closed cycle. So really, it's more of an open cycle in terms of the thermodynamics. You put in heat, primarily in the form of latent heating, and then release that latent heat here, which lowers the pressure, which drives the circulation. So, in fact, Kerry, in some of his later work, Kerry Manuel, has really talked about, the engine, right, is the ocean surface, right, in this model. So I think that's, yeah, this is a simple idea, but not probably, if you push it, it's not completely accurate. So.
I think that Kerry Emanuel himself usually recently explained this mechanism as like a system similar to the Carnot cycle engine. It's not the exact, Carnot cycle engine.
Yes, exactly. I think the main, I guess maybe one of the key ideas to come out of this is the conversion of heat energy into kinetic energy, right? So in that same way of like a thermodynamic engine. In fact, Olivier Paul-Louis from NYU, he wrote a recent paper talking about what he calls the steam cycle, which you can redo the Carnot cycle in terms of moisture, thinking about it. So the Carnot cycle being sensible heat transport and conversion, and the steam engine being latent heat transport. And so in the case where the atmosphere is saturated, they are almost the same. Yes, maybe that's a long answer, but yes. Actually, so I guess that leads to my second point here, is this recent paper by Roger Smith and Mike Montgomery. They actually have several papers along this vein that show cartoons somewhat like this. If instead of thinking about it in a thermodynamic context, we can think of it in a dynamic context, that if you have a secondary circulation largely driven by latent heat release in the eye wall cloud, also friction will drive an inflow response here, right? You have a three-way force balance in the boundary layer that drives the inflow. Then that inflow will converge angular momentum from the outer environment, right? And then, so if we rewrite the tangential wind, swirling wind, as m over r minus 1/2 r squared. As r decreases, if m is conserved, so angular momentum is conserved above the boundary layer, there are no pressure torques there, or very few, then v goes up, right? So that's a very simple mechanism to think about how the hurricane can spin up. Now, one thing they argue in their paper is that down here in the boundary layer, you do lose angular momentum due to friction, so there's a loss of angular momentum. But if it depends on this ratio, if m is being lost slower than r is decreasing, then v can actually still go up. And they argue then that there are sort of two primary mechanisms. One that was first talked about by Vic Oyama back in 1969 in his classic paper about this idea of angular momentum conservation and convergence due to heating. Right? So this is a balanced response to heating in the eye wall. This is a very efficient mechanism for intensifying the storm because there's no loss to them, right? But down in the boundary layer, there's a second mechanism by which this also happens. And in fact, the strongest winds are typically found in the boundary layer, as I showed yesterday from the dropsonde composites that tend to see a super gradient jet at about 500 to 700 meters where the winds are the strongest. And so Smith and Montgomery argue that that mechanism is also equally important, so that that strong frictional inflow also helps to spin up the storm. Even though friction itself, of course, is losing angular momentum, and it can actually, in concert with the heating. If you take the heating away, of course, friction will just spin down the storm. But if you have heating in combination with frictional inflow, you can spin up the storm very quickly. Okay? So that's the basic idea behind that. Now the key question is, why do some storms rapidly intensify and others do not, right? And I think we still don't know all the answers to that. But we have some ideas. So this is a nice figure from a paper by Pendergrass and Willoughby. There's also some similar work done by Vai and Schubert in 2009. They used the Sawyer-Eliason model. So when I talk about here a balanced response to heating, if you put a heat source here in a rotating frame, you'll get two gyres, one that goes like this and one that goes like that. So you get a gyre in the secondary circulation like this. That's part of what causes the eye, in the warm, dry eye in the center, and also what leads to the eye wall cloud and the inflow. So what they did with the Sawyer-Eliason model is use that balanced framework, and then put in prescribed heat sources at different locations. And so if you remember yesterday, I showed you some pictures of the Shea and Gray, where we normalize with respect to the RMW. You can kind of think of that as the same thing here. So this is radius, here's the radius of maximum wind, and then they put the heat source in, and then each of these different lines represents slightly different assumptions about the vortex. But the top line here is pressure change, so pressure expressed as a non-dimensional function, the Exner function. So pressure change and then tangential wind change. And you can see that depending on where you put the heat source makes a huge difference in terms of the intensification efficiency. So if you put the heat source way out here, then you still get some positive maximum wind tendencies, maybe 5 to 15 meters per second. But if you can get it very close to the radius of maximum wind, or even better, inside the radius of maximum wind, in fact, the strongest intensification rates are found if you can put the heating just inside the radius of maximum wind. So that's the area where the vorticity is the strongest. It's also the area where the inertial stability is the highest. And so Vai and Schubert talk about this in terms of a heating efficiency argument, that heat can be more efficiently converted into and essentially trapped inside the eye and lead to more rapid pressure falls. So if you think about it, this is the wind response, but then the pressure response is the same. That's on this axis here. So you see you get much faster pressure falls if you can put the heating in here. So this is similar to some of the work we saw yesterday, thinking about where to put the heating with respect to how the vortex size grows. But in this case, we're thinking about it in terms of the intensification, right? But so as we showed yesterday, that if you put the heating, in close here, it really doesn't change the size too much, but it has a big impact on the intensification, right? So this is just a simple, relatively simple model, and there's some theoretical work that supports this. But Rogers et al., Rob Rogers wrote a paper. I like this figure from his paper. This is a composite from airborne Doppler radar for a selection of intensifying tropical cyclones. These are all from the Atlantic, so hurricanes and steady state hurricanes. So the colors here represent vertical vorticity. So you can see it's a normalized radius axis, so R divided by the RMW. So 1 is the RMW, same as here. And you can see that, I'll talk about the colors first and then talk about the bars for a moment. So you'll notice a couple of things that are different between the vorticity structure. First, the vorticity is maximized inside the radius of maximum wind, but it's not maximized at the center. It's maximized around 0.6. So this is what I talked about on Wednesday briefly, which we'll cover again, is this ring structure of vorticity. So a minimum of vorticity here, maximum outside, away from the axis of rotation, and then decay of vorticity out here. In contrast, the steady state storms tend to have that maximum closer into the center. Now, this is radar composite, so we can't necessarily always get red in here, and it's a composite. So, but in general, you can see that this is closer in, and so this has more of a monotonic profile. There is a slight change of sign here, but for the most part, it's a negative gradient of vorticity going out. You'll also notice that in this composite, the vorticity is actually lower out here, so the tangential wind drops off more quickly out here in the intensifying storms than it does in the steady state storms. So we see a twofold change in the vorticity. One is the ring structure versus the monopole, and then two is the outer vortex structure. So we know that that is the case from composites and also from individual storms. The black line here represents a frequency. So this is frequency on this axis. So this is height here, by the way. That's for the vorticity. For this is frequency, and this is the frequency of convective bursts. So they use the radar reflectivity to determine where the convection was fired in these storms. And so you can see a very clear shift in the distribution, that there's a higher percentage of convection occurring at or just inside the radius of maximum wind for the intensifying storms versus outside. You can see the peak here at 35 is about 1.3 compared to 0.8. So that's consistent with these ideas about the intensification efficiency. So, so I think this picture is starting to emerge as one of there tends to be a lot of agreement between this, and I'll show you some of the results later on that are consistent with this idea. But that the radial location of the heat source, or the radial location of the convection, is one of the primary ingredients that determines whether the storm will intensify rapidly or not. Okay? There are other factors as well, but that's a big factor that we've learned from the airborne Doppler analysis. Now the key question is, and the thing we're still trying to work on, is why that happens in some storms versus others, right? Well, at least we've started to identify that mechanism. Okay, so you know, here's just one example of that leading to the rapid intensification. This is Rita, and this is radar reflectivity from Key West radar. So you can see Florida here. There's Miami. Rita intensified rapidly as it went through the Florida Straits right between Cuba and Miami. And I just wanted to kind of show this as an example of thinking about heating relative to the radius of maximum wind. So this simple snapshot of this is 09, 17, and 02Z. So that's basically from this blue line to about this blue line. So this is that intensification from about 60 knots to around 110 knots. So about 40 knots or so in about 24 hours. So very strong intensification. But you can see it at the early time, right? We definitely see organized convection. I mean, this is a hurricane, or close to a hurricane. It's just shy of a strong tropical storm. Very clearly organized rain bands. But if you look at the eye wall, it's somewhat disorganized, right? It's elliptical, sort of elongated. But then as the storm intensifies, we can see that we get well-defined eye wall that starts to form with that heating taking place very close to the radius of maximum wind in a symmetric sense, right? And then, of course, by the time we get to here, we have a very well-defined tight eye wall, right? So we're still looking at this analysis. We actually did have the P3 in here, the NOAA P3, NRL P3. This was during RAINX project. We weren't able to fly at this time because of the restrictions with airspace. NOAA got a permission, but the Navy did not. So we do have some nice observations, though, and actually we've done some preliminary GBVTD analysis from this. It's kind of interesting, but it's not really ready for prime time. So
how far is the distance from the Key West radar to the center?
It actually passed very close to the Key West radar. So Key West radar is right here. So this is a radar composite that combines Miami and Key West together. But yeah, fortunately for Key West, here, yeah, on this one. The actual strongest winds did pass south of the island. But,
so it is within a coverage of Doppler velocity?
Yes, it is. So yeah, so it's quite good. So, and then a little bit of some limited airborne Doppler. Okay, so so we think about this intensification process. Then you know, a lot of it depends on what's going on right at the eye wall, and especially right at the eye wall interface. I think that the subtleties of the heating in that region are quite important. So I wanted to show an example then. So let's imagine that we've now had this intensification occur, and in fact it can occur quite quickly. Here's some examples from Marks et al. 2008. This is Hurricane Hugo. Some of you may know the story about Hurricane Hugo. It's 1989. So I'll start with the same wind and central pressure here. You notice that it went, this is 12, 15, 18 in terms of time, from the 10th to the 24th of September. You can see an incredibly fast intensification up to about 75, almost 80 meters per second. Very fast pressure fall. This was 1989. We had satellites and things, but we didn't have quite all of the same tools that we had today. So the hurricane hunters decided to go fly Hurricane Hugo. This is 1710, just before this point. They went in thinking that they were going to fly Category 2 or 3 storm. They did not know what the intensity was at that time because they didn't have very good coverage. And it turns out it had rapidly intensified overnight. And this is the flight track here. They went through this eye wall. They actually made a very bad mistake. They decided to change the flight plan. They were going to go in at 10,000 feet and then drop down to a lower altitude, 1,500 feet. But they decided, well, it doesn't look that bad. We'll go in at 1,500 feet. So they went in at a very low altitude. And they ended up damaging the plane. They went through, this is, the white here is 52 dBz. So as I mentioned the other day, about 40 dBz is where you don't want to, you want to be careful. Anything above 40 is quite impressive. But they had not really gone through something like this before. So they've been flying for many years at this point in the 80s without any incidents. So they went through, here's a zoom in of that same thing. You can see this very strong eye wall. And unfortunately, they lost 3 of their 4 engines. Three of the 4. And so if you remember the picture I showed you of the P3, you've got 2 on one side and 2 on the other. So if you only have 1 left, that means you can only turn, right? You can't fly straight. So they were very lucky. They had extreme turbulence. So I'll show you what this looks like. This is the path. So this is radio cross-section. So this is time, but you can also think of this as radius. This is the radar reflectivity. Here, they had the airborne radar pointed they were just doing vertical and down, or vertical pointing. So here's altitude in kilometers. So they just had the radar pointed up, so you can see where they were flying. This is the aircraft flight path right here. Okay. So they, the flight track was at 450 meters. So you can see, and then the contours here are vertical motion. So the Doppler, if you're pointing vertically, the Doppler motion is just the vertical motion, including the fall speed of the hydrometeors. So you can see the stratiform rain. It doesn't look too bad here. And then here's the eye wall, though. It's 45 dBz. And then if you look at the updraft, you can see the updraft is concentrated right on the inner edge of that eye wall. Kind of very sharp gradient right there. Downdraft here, but then some of that is due to the hydrometeors as well. So keep that in mind, that it's a combination of the fall speed and the vertical motion. if we look at the flight level path, so let's start with the pressure. That's the red line here. You can see the pressure was falling and then has a very steep drop. Central pressure around 930 or 925, I guess, something like that. Here's the wind speed, and I find this quite incredible. The wind starts here at about 25 meters per second, and then it ramps up, and you hit, this is 80 meters per second here, so that's about 90 meters per second. And then look at the gradient on the inside edge here. It goes from about 85 meters per second down to 20 in just a few hundred meters. It's quite incredible. It's a sheet of vorticity here. The theta E is also quite impressive. You see the theta E go up. The theta E equivalent potential temperature in the eye was about close to 375 Kelvin, so very warm, moist air. And then the last one here is the vertical motion. So you can see that it's not too bad here, but then you start, this is where the plane started again. And so this updraft here, that's 20. You know, so, but I think one of the key is not just the updraft, but then the subsequent downdraft was also were on the order of about 10 meters per second. So the plane was subject to very rapid. So this is 1 minute from 1727 to 1728. So about a minute, maybe a minute and a half, they went, you know, like this at 450 meters. And like I mentioned, they lost 3 engines. Fortunately, they were able to get into the clear eye and start to circle, and they had just enough power, and also because of the calmness there, they were able to circle and climb an elevation slowly. But I've talked with many of them. There's also a nice description of this event from the former flight director. The flight director is now he owns Weather Underground, if you ever go to Weather Underground site in the US. So he quit after this and decided to start an internet business. He's a super nice guy, Masters, Jeff Masters is his name. So Frank Marks, who's now the director of the Hurricane Research Division, was on this flight. Jim McFadden, who's the director of aircraft operations, Pete Black, several other very prominent scientists were on this flight. And so they can all tell you good stories about it. But they were very lucky. They did manage to climb. And then the Air Force was there at the time. The Air Force used their radar to find a soft spot in the eye wall to help them then get out. And then they aborted the mission, as you would expect, and went home. But I think that I'm glad that Frank Marks was able to write this paper, and because we'll probably never get data like this again unless it's from an unmanned aircraft. So now the rules have changed. They won't fly below 5,000 feet in an eye wall, and typically they will go in at 7,000. Even if they're going to do the 5,000 feet, they'll go in at 7,000 feet first and check it out beforehand. So the mistake that they made was, underestimating the storm on the first penetration. So they now will go through. Now you may ask, partly why did they lose the engines? Part of it was this turbulence, right? But also part of it was that they actually they encountered one of those mesocyclones. If you remember the picture I showed yesterday from Hurricane Debbie, these mesocyclones, they can form, and in fact they can be very small scale. Dan Stern has done some numerical modeling on this, even mesocyclones, on the order of 1 or 2 kilometers across. And they actually had some evidence for what those look like in the radar reflectivity. So this is the tail Doppler radar data as it goes into the storm. So this is 34, 46, and 52, so it's about 30 seconds. So remember, this is flying into the page, radar standing like this, right? So there's the eye wall here, and so it's opening up because you're flying through the eye wall, right, as you get closer. But the dashed lines here indicate these sort of striations or these reflectivity features that are found at the edge of the eye wall. And I don't have any photos of it, but you can sometimes see these in the eye wall photos. They look like tubes in the eye wall cloud that are going around. So right in this extremely strong gradient, you have obviously a lot of vorticity, DVDR, right? It's V over R, DVDR is the vorticity. And so in that strong gradient, you can get stretching of vorticity and form very tight mesocyclones, and they believe that that's what happened, that they hit one of those, essentially like a tornado in the eye wall. I mean, you can kind of think of it in those terms, not the same mechanism as a tornado, but like a tornado. And so I think there's still some very interesting things that can be gleaned from this data. Also from ground-based data where we see some of these as storms come on shore. You can actually see some of these sometimes in the Doppler radar data as well. So there's some evidence that in Hurricane Andrew that some of the strongest damage was caused by one of these as it came on shore in part of the eye wall.
May I ask you,
Yes?
what's the degree of a slope of eye wave?
It's typically about 20 degrees or so from
20 degrees from Baltimore?
yes. So
About 70 degrees.
yeah, about 70 or so. But there's a lot of variation in that, especially depending on whether it's a small storm or a big storm. So some are more upright, and others are like we talked about yesterday. The outer eye wall can be much more sloped. So
Yes.
yeah.
But how about in this case?
Well, let's see. If you just kind of eyeball this here, I mean this. So this is to scale. So it's would you put that maybe 65 degrees, 70 degrees about.
And so you showed the dashed line means vorticity.
Well, this is just radar reflectivity, so we can't do a dual Doppler analysis from this. They had Doppler, but only vertically pointing. We don't have the vorticity that accompanies this, but I guess it's really pointing to these individual features in the reflectivity that they also view visually as sort of protrusions or tubes, vortices along the edge of the eye wall. So we did have a paper that I wrote with Sim Aberson and BAMS in, when did that come out? 2007, 2008, where we did a dual Doppler analysis of something like this for Hurricane Isabel. And we were able to see that strong vorticity. Yeah, so we have evidence from other storms of that, but not from this one. So,
Which is the eye wall that the airplane was penetrating?
It would have been, I mean, basically this part right here is, so where they drew this dash, so this is 1727-34. So if we look at that, that would be, I mean, that's this period right here across, so from 34 to 56. So that's basically the 3 scans that occurred during that time. So when they really hit the strong turbulence, they were flying through something like this.
So the fluctuation of vertical motion is not only associated with the eye wall updraft and downdraft, but also the mesos vorticity.
Yes, I believe so. Yes, and in fact, in Dan Stern's new simulations that he's shown, these features can be they can be quite shallow, but very intense, and then they rotate around the vortex at a speed slightly slower than the.
It's a vertical vortices, not a horizontal vortices. That somebody said where the horizontal road.
Yeah, I think there are some of those too, in fact, but in this case, I think we're taking about coherent vertical vortices. Yeah. So yeah, so with this display, you can't see the vertical structure of the eye wall as they're going in because of the way that the scanning was done. So you could see it on the nose radar. I mean, so that's basically what this was from the belly radar. So that's what it looked like going through. So they did pick the strongest part of the eye wall to go through. But that was also because they were flying from Miami. So that's just where it happened to go. And now I should mention that Hugo ended up making landfall in Charleston, South Carolina, caused a lot of damage there as a Category 3. It put a tree through my grandfather's house, through his roof. So it has a personal impact as well. So I think I guess maybe one other takeaway from this is that I think there's still a lot to be learned about the detailed structure of the eye wall. We don't have very many we have a lot of radar observations, but you know, there's a lot of variability, and so we need more research there, I think. Okay, so so I want to shift gears a little bit then and talk a bit about the structure more in general terms, and then we'll talk a little bit about Hurricane Rita again. So this is a nice picture adapted from Willoughby, but then is from Bob House's paper. I should have meant to put that there. But you can imagine, if we think about the structure, so we just talked about the eye wall, right? We can also imagine, we can break this sort of into different types of rain bands as well. So we could have something like a secondary eye wall here, or secondary rain bands, primary rain bands, what we often call the principal rain band. So that's one large quasi-stationary rain band. And then out as you get farther out from this sort of arbitrary interquarta environment, typically around 2 times the RMW, or 3 times the RMW, depending, then you may see more cellular convection or even organized squall lines, mesoscale convective systems. But we've known actually partly from airborne radar. So this is rain band observed by aircraft penetration of Hurricane Floyd, 1981. This is from a paper by Gary Barnes, who was at my department in Hawaii until recently. He just retired this year. Wish him well. And but he showed this is a great paper showing the structure of the eye wall and a rain band here from the aircraft reconnaissance. So here's the track across this large principal rain band here. And if you look at a vertical cross section, then this is from 0 to 8 kilometers, and radial distance to the storm center. You can see that the convective elements are in fact sloped outward, radially outward in this region here. About 35 dBz, so strong, but not as strong as what you might find in the eye wall. That convective element is surrounded by a lot of stratiform precipitation. So you see these sort of convective cores here with lots of stratiform. And so indicative of the stratiform